All right, good. All right, hey, welcome everybody, both I guess in person and online. Let's keep going. I think I mentioned that we've got 3 chapters on thermodynamics here, and so this is the start of our second one. And so let's jump in here and see where this takes us here today. So I'm going to put here chapter 14. And like I said, it's our second chapter on thermal dynamics. And maybe the best place to get started here is kind of with a little picture of something I'm sure you've kind of already familiar with. You don't need a physics class to tell you what would happen if you took a hot object and put it next to a cold object. And I don't actually have a hot object, but for demonstration purposes, I decided to go ahead and just grab what I'll call a hot object. So here's my piece of aluminum, and I'll put it right next to a piece of brass and just kind of push them together. What would happen? And I'm sure you know that whatever this initial temperature is of the hot one would begin to go down, and whatever the initial temperature of the cold one is, it would begin to go up. Now, the early scientists then said that there was a movement. They didn't really understand what it was. They just said something must be then transferring from the hot one to the cold one. Which is kind of a fun history in itself. And they're not wrong, but they went ahead and they called that heat. And they thought of it as kind of a liquid, kind of like, water would flow from one container into another. Because again, a lot of the properties you can measure, like how quickly does it flow, how much flow, there's a lot of identical properties, and so they were convinced that it was some kind of fluid. Now, I say that because one of the very first statements that you'll see in chapter 14, I think sounds kind of funny by today's standard. They say, what is heat? Heat is a form of energy. And given what we've already done, that I think seems obvious. And in fact, I'll just go back to what I've showed you many times. What is the difference between something that is cold and something that is hot? And so if it's cold, we've got these atoms bouncing around at a slow rate. But when we warm it up, they look like that. And so, of course, in your mind, you're saying, well, if the temperature goes up, it has more, and you might call it internal kinetic energy. But see, there it is. It's a kinetic energy. And so it doesn't surprise you when I make this statement that heat is an energy. But I do want to emphasize, to the early scientists, that was like a big surprise. That was part of, or one of Joule's famous work, is he looked at this and he says, whoa, heat isn't anything new or different. It's just a kinetic energy of the atoms down inside. So here's what I'm getting at. Our definition of heat is going to really then just be the amount of energy that flows. So I'll just put amount of energy. How much energy went from the hot one to the cold one? And of course, the hot one is losing energy, so the molecules slow down, and that is related to its temperature. And then the cold one, of course, gains that energy because of conservation of energy, and its temperature goes up. So like I said, this first step isn't really, I think, too much of a surprise to you, because we've been looking at heat already as the internal kinetic energy. But what it does lead to this idea is that if you took some material, let's say aluminum, and maybe a different material, let's say brass, and I'll pick on those two because, again, that's what I have right here. You could ask then, what would it take to raise the temperature of aluminum? In other words, how much energy would it take to raise it? And I'm sure you would ask, well, how much? Because obviously if you raise it 1 degree, that's going to take less than 2 degrees, which is going to be less than 3 degrees. Okay, so it must depend upon how much you raise it, not the material itself. So let's just say, to keep it balanced, let's say how much would it take to raise 1 degree? All right. Then we could also say, well, what if I had a lot more brass than aluminum? Those of you who did the lab in person yesterday know you guys weighed these, and the aluminum was somewhere around 92 grams, but the brass, I think, was in the neighborhood of 300-ish. Yeah. And so we just have a lot more brass. Here's what I'm getting at. We would like to ask this question: how much energy does it take to warm these up? And since they're different materials, we would kind of expect the answer to be different. But I want to emphasize that it's different because of the material, not just because we have more material or that we warm it more. This is, yeah.
Is this kind of like alluding to the specific heat capacity?
Yeah, so you got it. This is exactly what because we did the lab one step earlier. I'm getting at the definition here of another fancy word that'll become very useful, and we call this the specific heat. Specific because how much is related just to the material. The symbol we like to use for specific heat is the lowercase c. And it would simply be this: the amount of energy, and I guess I'll say slash heat. So how much energy does it take to raise 1 gram 1 degree Celsius? That would be sorry. I wanted to be careful here. I didn't want to say gram. Let me use your author's definition. Your author says in words, he says the amount of heat needed to raise 1, and he uses kilogram in his table. And sometimes people use per gram, and that's what we did in the lab. And some use kilograms. And your author is going to use kilograms. Let me remove this for a few moments till we need it. Doesn't block your view. But here, and you touched on it, good, is that using this name, this is a property of the material. This is saying how much energy would it take to raise 1 kilogram 1 degree. And as you'll see here in a second, we'll look this up, it's different for the different materials. That's why you guys did the lab, and you guys online will do the lab, where you are asked to measure how much energy does it take to warm up, and then we used lead, and we did brass, and we did aluminum. Now, in symbol form, it would look like this. The traditional symbol for heat is Q, not to be confused with our fluid dynamics Q, where we did volume per time. But the amount of energy is Q. Of course, the traditional symbol for mass is M, and the traditional symbol for a change in temperature is just delta T. So writing it out of the formula, it would look like this. But conceptually, it's just trying to say how much energy does it take to warm something up. Or let me not forget about the reverse. If it cools down, it's got to then release that much energy. So your author starts off, and I'll pick on aluminum since it's at the top of the chart here, but it says 900. it says it takes 900 joules to raise 1 kilogram 1 degree. And the reason that can become useful is if you rearrange this equation, which is often of our interest in how much energy do you have to give the aluminum or take out of the aluminum in order either to warm it up or cool it down. And so I'm going to put a box around this equation, even though this may be the definition of specific heat, and that would be nice that you kind of remember it as the amount of energy based on the material. That is, it is per kilogram per each degree. So it's factoring out how much mass you have and factoring out how high you raise the temperature, and so it only has to do with the material itself. And so aluminum has a specific value, and as we can see in this chart, that value is 900 joules. If we go to brass, and I don't think they have brass listed, but since brass is mostly copper, let me pick on copper. And so copper here is much less, somewhere between a third and a half here. And so again, if I had 1 kilogram of copper and I was going to warm it up 1 degree, I would have to give it 387 joules of energy to warm it up. And so you might say, oh, it's going to be easier to warm up copper compared to aluminum. And again, I don't know if easier is such a good word, but it takes less energy to warm up 1 kilogram. So each of our substances has a given value, and so note then as we work with our substances and as you do the homework problems, and as you guys at least in person already did the lab and you guys online are about to do the lab, you begin to see that there is a different feature to this, or a different number. In fact, a good one to look at is water. Especially for you guys in the life sciences, since most of a, say, human body, here's a human body, is water. And so here they say it takes 3,500 joules to warm up 1 kilogram of body tissue. Now water is going to be a little higher than that. Yeah, here's water at 4,186. But water's a big number. That's what I'm getting at. It takes a lot of energy to warm up water. And that's the number that I want here to point out. In fact, this is kind of helpful then to pause and go back in history a little bit before scientists really understood that heat and energy are the same thing. They said, well, we need some kind of unit for heat. In their mind, they go, well, we can't use joules because joules is for energy, and heat's not an energy, or we don't know if it's an energy or not. And because of that, then, they said something like this: let's use water as our reference point. In other words, if I had 1 kilogram of water, how much heat energy would it take to warm up 1 kilogram of water 1 degree Celsius? And that then became their specific heat. And it became the definition of what today we then call a calorie. And that's calorie with a capital C. Because they realized that if you're working with something like a human body, you need a lot of energy. But if you're working with something small like a test tube, you're looking at me like I'm crazy, Ron. If you're working on something small, then we'll do this: 1 little calorie per gram per each degree. And I got to admit, and I think you're going to admit too, that's kind of obnoxious to have a capital C and a lowercase c. So from a science perspective, we get away from the capital calorie and replace it with a kilocalorie. Because you can see that this must be 1,000 times bigger because we're talking about 1 kilogram versus 1 gram. But here's what I'm really after then, is the definition of a calorie. Because even though I would say calorie is not part of the metric system, it is still very useful and it's used a lot. And I know you've come across it a lot. And so if I had, and I'll just put over here, 1 gram of water, and I warm it up, let's say from 20 degrees to 21 degrees, and you asked how much heat did it take, this is easy in calories, right? It's just 1 calorie. That is the definition of a calorie. The definition of a calorie, right here, is how much energy does it take to warm up 1 gram of water at 1 degree? And that's what I'm asking. 1 gram of water warmed up 1 degree. So the energy you would have to put into this 1 gram is 1 calorie. Which then, looking at that chart, means it would be 4.186 joules of energy. And that's then the conversion factor I want you to understand. And again, you kind of have to go back in history to realize that before scientists realized that heat was an energy, they thought it was something else, some other quantity. So it had its own units. And so now that we know heat is an energy, there must be a conversion factor. And that's what I'm trying to give you. So 1 calorie is 4.186 joules of energy. So keep that in mind because we will come across different problems and they will sometimes give us energy in calories. And you'll need to go, wait, calories, how many joules is that? And so this is the conversion factor. Now, there's other problems, especially because this is focusing on the life sciences, where they will give you the energy in capital calories. That's what a nutritionist does. When you walk into McDonald's and you buy the Big Mac meal and the little sign says it is 12 billion, no, it's not that many. I don't know what a meal is. I'll just call it 1,500 calories. They mean capital calories. For us, let's call it a kilocalorie. But then, of course, a kilocalorie being 1,000 times this is 4,186 joules. Or kind of a fun thing to do here is, in a typical day, maybe a little more for you younger people, but I'll say 2,000 calories. And so, so a human needs about 2,000, and those are capital calories. So how many joules of energy is required for one human to try to function throughout a day? So I'll multiply this side by 2,000, and I'll multiply the other side by 2,000. And so I think we're looking at 8,372,000 joules of energy. And one thing you will notice, and I think it's quite surprising, is how much energy does food really have in it, and therefore human and living tissue really need. It's 8 million joules. I guess it doesn't sound so bad when you say 2,000 calories, but 8 million joules is a lot of of energy, which is why myself, mostly, really have too much going in terms of energy and not enough coming out. And because of conservation of energy, my body decides to store it and pack it in there. And so I need to learn to switch that up and use more energy than I take in. But that's the whole idea of dieting, right? The whole idea is to try to make sure that you then use and burn up more energy than you take in. Because, of course, from conservation of energy, your body has to get it somewhere. And that would be in the molecules or the fat tissue that's stored in your body. Well, I digress from our physics here, but I really just wanted to emphasize not only what is specific heat and how they're different for different materials, but what is the definition of a calorie? Because we're going to come across it quite a bit. And this leads to our first and very useful formula if you had something like this. You know, if you had the mass of the ocean and the specific heat of the water, and if the ocean warms up 1 or 2 degrees, you could multiply all of this and figure out, okay, that's how much energy must go into the ocean to warm it up 2 degrees. Or the other way around, how much energy has to come out of the ocean in order to cool down. All right, so that's our first step. Now, our second step is what we call the energy of phase transitions. And so your author does a pretty good job here of showing you a picture. Now, I brought him out again, and so I'll just kind of bring these here and say, okay, what is the difference between a solid and a liquid? And so the solid, they're hooked together, and of course they're at some temperature, so you got to kind of imagine these vibrating. But if you warm it up enough, they kind of break free, and so I don't want to do too much damage here, but if I shake that, see, it begins to come loose. And it would stop looking like that and start to look like this. So in other words, energy has to go into breaking the bonds, not to make them go faster. Now, this is important here because the energy doesn't always make the molecules go faster. Did you catch that? Watch. Your author has some really good pictures here and a nice little graph. And I think it's picture 7 here. He kind of shows the same thing I was trying to show, that if you have a solid and they're hooked together, as long as it's still a solid, as you warm it up, the molecules just go faster and faster and faster and faster. And that means the temperature goes up. And we could then calculate a connection between the energy and the temperature. And that's what this formula is for. But when we change states, when we go from the solid to the liquid, so when we go from, say, here to here, the energy breaks the bonds, but it doesn't make them go any faster. So what that means is you're putting in energy, but its temperature is not going up. And so that's what I mean by when I said we've got to look at another way of adding energy to our substances or taking energy out. And this really bothered the early scientists. They called this a latent heat, a hidden heat. They said, look, we're giving it energy, but its temperature is not going up. Doesn't that seem weird? And of course, hopefully it makes more sense now when you look at the microscopic level. It's not weird. You're just not making them go faster. You're just giving the energy to break the bonds. In fact, that's why I had this set up, and I'll now go back here to say, let's actually watch a simple experiment of breaking the bonds. I can put maybe a bunch of ice in this case, a beaker here. So I'm going to load this thing with ice. I didn't get it packed in very good. Let me put a little water on the bottom here so I can kind of. Yeah, that should be enough to get things started. So most of it is ice. And if I go ahead and put a flame on it, we'll begin to change phase. And that is, we are going to break the bonds, and the H2O will stop looking like this and start to look like this. But the real key here, as you already know, ice and water is at 0 degrees Celsius. And so even though I am adding energy to it, the temperature doesn't go up. So if you ever have ice and water together, you know its temperature, right? You know its temperature is 0 degrees Celsius. And yet, as we add energy, we break bonds, we don't make them go faster. I think your author does it better in this graph picture, which is if we were to put a thermometer in here, this is what we would see. If we say, let's plot the temperature on the vertical axis, and on the horizontal axis, we will plot the amount of energy we are giving our ice. And if our freezer is set, as they have it, at negative 20 degrees, when it comes out of the freezer at negative 20, when you first start adding energy to it, they vibrate faster and faster, and so their temperature goes up. And I would say at this point, we're doing something like this. We are adding energy and its temperature is going up, and that's true as long as it's a solid. But once it gets up to 0 degrees, something else begins to happen, and that's what I'm trying to emphasize. From here to here, we have a mixture of ice and water. And that's where I am right now. I have a mixture of ice and water. And even though I'm adding energy to it, its temperature isn't going up because the energy does something else. It's not making the bonds break. It's making the bonds break. It's not making the atoms go faster. And then hence the name latent heat, because it's like, it just seems kind of weird to the early scientists. You're adding energy and the temperature didn't go up. Where did it go? Question.
I'm just sort of confused. Like, okay, when it's solid and you're giving it energy to like convert it to a liquid, okay, if you just break the like bonds and their molecules are just the same next to each other, it's liquid. But when you give energy to a liquid and you convert it to a gas, like you know that the molecules in gas, they have more space and they're just moving faster than a liquid. But you're saying that when you're giving energy to a liquid, you can't like it's the molecules are not moving faster. You just break the bonds. But in gases, like the molecules move faster than a liquid.
Okay. Yes. Okay. Good. I'm glad you said all that, because that's exactly where I want to go. Maybe I'll keep talking here. So what will happen is at first these will break. And so if you can imagine, half of the bonds are broken and the other half aren't. As long as I keep adding energy, I just keep breaking the bonds until all of them are broken. Now, I also want to be careful. I didn't fully break the bonds. When you have a liquid, you will see that they are still semi-hooked together. Okay, so I think what you're getting at is once I turn it all into a liquid, and so that's on this graph would be this point, then as I add energy, the atoms start going faster and faster again. And so the temperature goes up and up and up, but notice it says it all has to be water. Okay, and I'm almost there with this little experiment. I've almost broken all the bonds. So right now we're still at 0 degrees, but in a little bit, all the bonds will be broken, and now we'll start to make the atoms go faster again. And then when we get to 100 degrees Celsius, I think this is what you were getting at. Yeah, at 100 degrees Celsius, we start to break bonds again. We do a full breaking of the bonds. So back here, when we went from a solid to a liquid, you might say we broke half. I don't want to say half the bonds. That sounds like only half the bonds. But we broke half the strength of all the bonds. How's that? And so we went from them being rigidly connected together like this to what I'll call quasi-connected together. But then when we get at some, in this case, 100 degrees Celsius, we're going to be fully breaking the bonds. And now it'll look like that. Okay, so when we get to 100 degrees, there's going to be another latent heat. And that's what is trying to show here. In this process, while you are boiling the water, okay, and I'm still a long way from boiling, but it'll get there pretty quick. Once I start boiling, what is happening is I'm adding energy to then completely break these. And in this picture, it would look like this, that I would shake it so much that they would go, whoop, there it goes flying out. And another one, right? And so, whoops, I didn't mean to do quite that many. But they would fly apart, and that's where the energy is going. And so during that transition, where it is boiling, the temperature never goes up. So if you ever see boiling water, you know it's at 100 degrees Celsius. You could have a little water or a lot of water, but all you're doing is adding energy to make it escape, if you will, to make it break off. And so that's the second part of this chapter, is the energy not associated with temperature change, but the energy associated with the phase change, the part that is breaking the bonds. So it looks like, by the way, that in my little experiment, we have gotten to the point now where we are doing this part of the curve, where we are now having water and we're warming it up. We have not quite got to this point yet, but nonetheless, we got that far in our discussions. Anyways, the fancy word I was using here is latent heat. And maybe the word now makes sense to you because of the history of the early scientists going, that's just weird. You added energy and it didn't get warmer. And so I want to emphasize that. I guess the definition I would put here on the board is the energy needed to change state, or your author uses the word change phase. And we'll list it as 1 kilogram. How much energy does it take per kilogram? So, in other words, this would be a Q, because it's heat, divided by the mass. And I know in my little experiment it's already changed, but if we went back to the beginning and said, all right, I have, and I didn't measure it accurately, but I can kind of see here on the beaker that I have 400 grams. So I must have put 400 grams of ice in here, okay, which would be 0.4 kilograms. But if I were to measure how much energy did it take to melt that ice, not raise its temperature, but just melt it, just go from 0 degrees ice to 0 degrees water, and then I would divide it by its mass, which in this case would be 0.4, I would get what we're going to call the latent heat of fusion. The little f stands for fusion. And don't let the word confuse you. My approach was to go from ice to water, and you're thinking, well, that didn't really fuse it together. But the name comes from the fact that normally at room temperature, you start with water, and to make ice, you have to take the energy out to fuse the water molecules together. So there's where the name comes from. And so I'll just say that if you started over here with warm water, you'd have to take energy out to cool it. Then, even when you got it to 0 degrees Celsius, you still got to take a lot of energy out to fuse it together. And that's why if you ever make ice in your freezer, you'll know that you take the little ice trays, you pour in the water, you put it in the freezer, you close the door, and it gets cold right away, but it doesn't become a solid for a long time because it's going to take a lot of energy to come out. And if you go back after a couple of hours, you might find that just the surface of the water has turned into ice. And so some of it has fused together, but not all of it yet. And so you have to wait a little bit longer for the energy to come out. And so again, that's called the latent heat of fusion. Now, as you pointed out, there would be also a scenario where we go from the liquid to the gas. And it looks like I'm just about there for my experiment. I see little bubbles beginning to form. In fact, I guess I would say I'm actually just got there. I would say I have now warmed it up, and I would, on this graph, I guess I'm right about here, where I've given it enough energy, the molecules have now gone faster, and now they're beginning to break apart. And now the energy is not going into making the atoms go faster. The energy is going to break the bonds. And so again, to figure out what the total amount of energy is, I have to account for not only did it warm up, but it changed phase. And so now I'm at this place where it's starting to change phase. And you can see the little bubbles form there. And that's called the latent heat of vaporization. So I'll put a little V here and put in here vaporization. Latent heat of vaporization. How much energy does it take to break those bonds? And your author, of course, not a surprise, lists this in table 2. And so where is water? And so water here takes 334. And let me scroll up here to do a better job here of the units. There we are. I didn't go up high enough here. But, well, now I can't see the water, so maybe I'll put it over here. But it was 334, and we have 2 columns. That's because we can think of it in joules or kilojoules per kilogram or kilocalories per kilogram. So here he writes it as 334 kilojoules per kilogram. I kind of like that because you can easily also cancel off the kilo and you get joules per gram. Now, of course, you'll notice that he also listed it in calories. And so it's 79.8 would also work. And so 79.8 calories per gram. Or if you put a K in front of each one, top and bottom, it's kilocalories per kilogram. And so, like I said, we can deal with our energy in either joules or calories. And like I said, even though calories seems like old school, not part of the metric system, incredibly useful. And so we still have it, and that's why we convert. Now, if you look at the latent heat of vaporization for water, where's water? Right here. What was it? 2,256. So 2,256 kilojoules per kilogram. or 2,256 joules per gram. Or we could do it in calories, but I'll let you look that up if it's needed. Now, here's what I'm getting at. This energy is a lot to change from a liquid to a vapor, into a gas. And coming back here, you can see in my experiments, I clearly am at a boiling point now. But it's going to take a lot of energy to boil all that away. So, we won't wait the whole time for it to boil away, but I do want to then use this as a chance to say, maybe we should calculate how much energy did I give my, and in this case, 400 grams of water in order to first warm it up. And I'll just tell you, we got the ice out of the freezer. And so as that graph was trying to say, we were at negative 20 degrees Celsius when it came out of the freezer. And so the first thing we had to do was warm up the ice to 0 degrees. And so if I were to say, okay, what is the total amount of heat energy that I need to give these 400 grams to completely boil it? And like I said, it's going to take a while before it's all gone, so I think I'll finish my calculation before it's all gone. But it helps me illustrate that what I need to do is an MC delta T, because I will call this part warming the ice. And after I warmed the ice, I would have then an MLF. See, that's this step right here. To get the amount of heat needed to change it from a solid to a liquid, I need to know what this number is, which is the amount per kilogram, and then how many kilograms do I have. And so this would be the energy to melt the ice. That did not make its temperature go up at all. Then, once I melted all the ice, I now had water that I had to warm up. So I have another MC delta T, and I will call this then a warming of the liquid water at this point. And then finally, once I got that liquid water warmed up to 100 degrees, and that's where we are now, I now am putting energy that breaks the bonds, which changes it from a liquid into a vapor. And so now there's going to be an MLV for then boiling it away. Or what I would say, breaking the rest of the bonds. Remember, when we went from a solid to a liquid, we only partially broke the bonds. Now we go the rest of the way. Okay, so keeping this in mind, here would be my calculation. So I need to know how much do I have, and that's when I said I have 400 grams, which I will change to 0.4 kilograms. I'll also need to know what is the specific heat of ice. And so let's flip back to our chart. I guess that was chart number 1 here. But I also wanted to take this as a moment because we did look up water in the liquid state, and it's tempting to think that it would be the same, but it's not. They're hooked together differently. And so if you look here, let me just check the units here. Right here we have ice. And it takes 2,090 joules per kilogram for each degree to warm up. So this would be 2,090 joules for each kilogram to warm up 1 degree. And of course, we're going to warm it up 20 degrees Celsius. So that would be my first term in my calculation. Just how much energy did it take to warm up the ice? Then the next part is right here. This 334,000 joules for each kilogram. So I will take the mass of 0.4 kilograms, and then I will multiply it by 334,000 joules. So I'm just going to put it in the same unit. So 334,000 joules per kilogram. And so that would be the second step in my calculation. The next step would be to say, okay, now we're going to warm up the water. All right. So I have 0.4 kilograms. And now I need the specific heat of liquid water. And as we saw earlier, that was at 4,186. It's down here. Very common number, probably worth committing it to memory. And so this is 4,186 joules per kilogram for each degree you warm it up. Yeah.
Where did you get that 20 for delta T? Like,
oh,
that 20 can be, like, delta can be in all of the water. That is like the water.
Right. Okay, so I got the 20 because the ice, and I'll show you in the chart here. I guess the short answer is I got it from the chart. The long answer is I know that we set our freezer at -20. So the ice, and to be honest, it's probably warmed up a little bit since it's in the room. But I'm just kind of imagining I just go to the freezer, I get it out. The ice is not at 0 degrees. It's colder than that. So before it starts melting, I've got to warm up the ice 20 degrees. So it has to go from -20 up to 0. So that's where the 20 comes from.
But it can be even more than 20, like,
Yeah.
it can be 10.
Right. It would depend, right, on how you set your freezer. You could set your freezer at -10, and it wouldn't be as cold. You could probably set it colder at -30. I'm not, yeah. So there's nothing special about that one other than I just wanted a number so I could show you the first calculation requires that we add energy to the ice to warm up the ice to 0 degrees Celsius before we start breaking the bonds. Which then helps me with this. So what number would go here? Yeah, right, 100 degrees Celsius, right? Because I know that I have to warm up the water from when I just broke the bonds, which is 0 degrees Celsius, until it starts boiling, which is at 100 degrees Celsius. And so I need to know the melting and boiling point of the substance, which in this case is water. And then finally, the fourth piece of this calculation is, again, what's going on right now. And you're going to see this is the most energy. This is the biggest piece of all of the energy, and that's why it's just going to take a long, long time for all of this to boil away, because it takes quite a bit of energy. And so I will put 0.4 kilograms here, and then I think I wrote it down, yeah, right here. This takes 2,256 kilojoules per kilogram. And maybe in passing I should point out that if, and I can't really do it, I don't have the equipment, but if I were to capture the water vapor, then I could start warming up the water vapor once I boil it all, and now the temperature can go up beyond 100 degrees, and I would have another term that would look like this, an MC delta T, if I were to warm the steam from, say, 100 degrees to just say 200 degrees, you know. So, but my setup can't do that. Once it turns into a vapor, it spreads out throughout the room. And so this is the best I can do. So I wanted you to see each and every piece of the calculation and point out that even though the temperature doesn't change, we have to account for that energy. So this first one, 0.4 times 2090 times 20 is 16,720 joules. And I have a feeling that's going to be the smallest piece of all of this. In other words, the easiest part of this is just adding energy to the cold ice to warm it up. All right, so then this one is 0.4 times 334,000. And so this is 133,600 joules. And so again, just want to emphasize, that's a lot of energy. That's just to melt it. You haven't even warmed it up yet. Now, to warm it up to a boil, 0.4 times 4,186 times 100. This is 167,440 joules. Now, so bringing it up to a boil is a little bit more than melting it, but you know, it's not too much more. It's only about, 25% more. And so the general idea here is that, hey, this is amazing that the same amount of energy it takes to bring water to a boil is the same amount of energy it takes to melt the ice. Well, then the last one here, this is, as the one I said, is by far the biggest piece of the puzzle. This is where most of the energy is. 0.4 times 2,256,000. And so this is 902,400 joules of energy. And look, these other ones aren't even close. And so if we add all these together, we get, it's like 1,220,000 and change. I'll just, for significant figures, just put it at 1.22 million. And so it's a lot of energy. And so part of me, I wanted you to see how much energy it takes to break the bonds. And then to kind of understand things like, all right, why would it take so long to make ice in the freezer? Well, this is why you got to get all that energy out. Now, for you life science people, the neat thing about that is, what if the snow falls in the mountains? When does the snow melt? It takes a long time to melt all that snow. And so even right now up in the Sierras, even though we're getting to late June, there's still lots of snow up there. Because it's going to take a long time. It's going to take a lot of energy to melt all that snow. And so that's this idea. Now, the reverse is true. Look at this. If you tried to then make vapor, that takes a lot of energy. But the reverse is also true. What if the vapor then turns into rain? Doesn't all that energy have to be released? And this is where the energy in storms come from. Big storms have lots of rain. They go together because the energy is coming from the condensation of those. And so where we live, our storms just aren't big. I know sometimes we think, oh, that was a rough storm. It blew down trees and flooded the streets. But there's nothing like a lot of rain in, say, in a hurricane. And so you have to be in the tropics or the subtropics to have enough moisture in order to condense, in order to have those powerful storms. We just don't have powerful storms at our latitude because we just don't have the moisture, and that's where it's coming from. And that's this whole idea. All right, well, with that in mind, I'll give you one more example and then we better move on, because this always just seems really weird to me, but it works. I actually have a friend who is a rancher, and when it gets cold, if it gets cold in Santa Barbara, they turn on the sprinklers on their fruit. And they'll listen to the forecast in wintertime in January, and it says, hey, tonight it's going to drop down to like 28 degrees Fahrenheit. Which, if you remember the problem we were doing, it was like, okay, that's the place where you start to damage tissue at that coldness then. And so plants, and particularly fruit, can be damaged. So the goal is, how do I keep my fruit from getting damaged from the cold? How do I give it energy? And I know this sounds silly, but he turns on his sprinklers. And all night long, he's just spraying water on all the orange and lemon trees. How does that keep it warm? I know when I'm cold, I don't want to get sprayed with cold water. But see, the ranchers realize that if you put a liquid on it, for that liquid to freeze and become a solid, wouldn't it have to release this much energy? And it would do that at 32 degrees Fahrenheit. And so as long as you're shooting water on the trees, as long as it's a liquid, you know it's above 32. And as the ice starts to form and it makes these little ice balls around the oranges, it's just kind of weird in the morning when you go out there and you look, because this orange now has a big ice ball around it. But see, all night long the ice was forming, and as the ice formed, it was giving off its heat and keeping that fruit at 32 degrees Fahrenheit, not letting then it get lower than that. It's also making a barrier that keeps the colder air away from it, and so if everything worked right, the fruit is still 32 degrees. And then the sun comes up. And then to see if it works right, you have to usually wait a couple of days to see if when it all melts off, if the fruit is still good and your produce is still good and you still have some livelihood left and some money left. And so that's really kind of the point here. All right, well, like I said, I better continue on, and I'll kind of shut this off and say, okay, we haven't boiled it all the way, but we, I think, get the picture here. Now, as your author continues, the second half, I guess, of this chapter is more of a discussion along these lines. And it says, okay, how does the energy go from one object to another? Now that we've just talked about calculating how much, let's go into the mechanism of how does it go from one to another. And so that's the second half of this chapter. And we call this then the heat transfers. And what you'll see here is there is three ways that energy can be transferred from one object to another. They're slightly different. They have different equations and different rates. But your author says heat transfer methods. And the first one I want to talk about and show you is called conduction. That's probably the easiest one to understand, and the easiest one for me to demonstrate, and the easiest one for us to calculate. The other one is called convections, and the last one is going to be a little challenging because we really haven't done our waves yet. That's the next section coming up after here as we come to the end of the semester, but it's called radiation. And I should be careful with that word. I don't mean like poison, toxic radiation, but let's talk a little bit more about that word. But it's radiation. Okay, So what is this first one? What is conduction? Well, I think your author does a good job here of kind of explaining it. So I'll just read what he says. Maybe I should make the words here a little bit bigger for you guys to see here, but man, it's not going to fit on one screen, is it? But it says here, conduction is heat transferred through stationary matter. And that's what I want to emphasize. The material itself does not actually move. The energy does. So watch, I'll keep reading. By physical contact. The matter is stationary. How does he phrase it? The matter is stationary on a macroscopic scale. We know that there is thermal motion of the atoms. Oh, I guess he's just kind of getting into the nuts and bolts. I think it might be better to come down here to a picture where he says, take a look here at a hot object next to a cold object. And so I will come back to where I started today's lecture and said, all right, imagine the aluminum is hot and the brass is cold, and you put them in contact. You see, the aluminum is moving fast, and the brass, which is mostly copper, is going slow. And so if you have a fast-moving object that bumps a slow object, what happens? Well, I guess the slow one picks up speed, hence gaining energy. That's our heat energy. And the fast one slows down. I like to draw it this way. I like to say, okay, here they are moving very, very fast. Here they are moving slow. And if you look at kind of one layer, what will happen is this first layer that is going fast will bump the slow layer. And so that slow one picks up speed, and then the fast ones slow down. But it doesn't stop there. If you look at a second layer beyond that, they're still going fast, and so they're going to then bump these ones that were fast but now have slowed down. So in other words, they're going to pick them up with speed. And the same thing is true for the second layer in the colder material. That is, that now that these picked up speed, they're going to bump the ones behind them, so they start to go faster, making them go slower, and so you end up having the ones at the edge going fast and the ones at the edge going slow again, and so they bump and the process just repeats itself. And it keeps doing this layer by layer, and so it takes a while, but the energy does move over. And so what we like to say is there's a movement or a flow of energy without actually a movement of the material. That's why in his definition that is in the book, I like how he starts off by trying to say there is not an actual movement of the material itself. And that's going to be the distinction between conduction and convection. And that's why I want to keep emphasizing it. So when, again, I take something like this, and I have a hot piece of aluminum and a cold piece of brass, and I put them together, these aluminum atoms stay here. Never do the aluminum atoms go over to here. And likewise, the copper atoms never go over to here. Yet, the energy does go from the aluminum to the brass/copper. And so there is a flow of energy without a movement of the material. And I should say, as he says, a movement on the macroscopic scale. I mean, obviously on a microscopic scale there's movement, but they don't leave each other. They just bounce off of each other. And so there is this flow. Now, your author then kind of illustrates it with this picture, and then the one below it. Maybe I'll stick on this picture for a second. But he just says this is going really fast, bumps into a slow one, and so what ends up happening is this fast one goes slow, and the slow one goes fast. If we go to his other picture then, he says this whole process could then transfer energy by saying, let's take something that is hot, so it kind of gives it kind of a red or a pink color, and something that's cold, so it gives it kind of this blue color. And he says, this atom's going to bounce and ricochet off of this one, which bounces off that one, which bounces off that one, which bounces. And the atoms themselves don't move across, but the energy does. And so the fast-moving one gives its energy to the next, 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 to the next. And so even though the atom over here did not go over here, the energy over here went to over here. And that's what he's trying to say. For me, I like to run this little experiment. This is what we call our conduction meter. It measures how quickly this process takes place. And what I want you to see is it is not the same speed for all materials. And so here's our conduction meter. If you can see it, maybe I'll kind of hold it this way. It's a hub that has a bunch of rods sticking out. And the rods are all burnt from years of putting them in the flame, but they are different. This one here is copper, this is brass, this is nickel, this is iron, and this is stainless steel. And the reason they're at a hub is I'm going to put them in the flame so that one end of the rod is going to get really hot. And that's what this picture is illustrating. So if this is the rod, this is going to be the flame. And so one end of the rod gets hot. And what I hope is going to happen is the energy is going to hit one atom at a time. And so I'll just talk about the copper one right here. And so the atom hits that one, 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 and eventually the energy ends up at the other end of the rod. And if you're wondering what these red things are, these are just candle wax. Because candle wax, when it gets hot, melts. And so this will be my indication of when the other end of the rod got hot. When it falls off because it melted, I know the other end got hot. And it's called the conduction meter because then we can compare the different metals and see which one gets hot first on the far end, and therefore the wax falls off. And so if I take my burner here and just kind of carefully get it in the flame, I can put it in here, and I'll say it again. I am getting one end hot, and maybe without giving away the answer, keep your eye on this one first. This is the copper. And copper and brass is mostly copper. Then we got nickel. Oh, well, and there it goes. And so obviously it got hot there on the copper first. The brass is soon to follow. Well, there it goes. And so the brass gets warm. Again, what I want you to see is all of them will get warm at the end. It's just a matter of how quickly do they get warm at the end. So they all conduct. And maybe I won't wait the whole time. Let's just see if we can get the nickel and iron. They're about equal. And the iron will go a little first. Okay, so there goes the iron. And then the nickel should be right next to it. Oh, there goes the nickel. And the stainless steel will be here till Christmas. So I'll leave that one alone. Well, not quite Christmas here. But there's the different rates. And I shouldn't put that hot thing on the table there. I think I left a little burn mark there. Anyways, you get the idea. In fact, here's kind of another fun experiment I like to do. I'd like to take something that has a poor thermal conduction, which would be this piece of wood, and compare it to aluminum. And so we didn't have those two materials here. But as we'll look on the table, the conductivity of wood is pretty poor. In fact, so is stainless steel. So I got stainless steel. But aluminum, it's really strong. So if I grab a cup here, and I fill this cup with ice, I'm going to plop this on. Heat is going to flow from the piece of wood into the ice, and it's going to melt it. But what I want you to see is it'll take a long time for it to melt. But it will melt. And the same thing is true if I plop it on the stainless steel. But one that flows really fast is kind of impressive to watch. And so this is the aluminum. And if you've never seen an ice cube on aluminum, I hope you're kind of impressed here. You could actually see kind of it turning to a liquid. I mean, the heat coming out of this chunk of aluminum and flowing into that is just amazingly fast. And it just melts in front of you. It kind of reminds me of late night commercials. We got the Frost-O-Matic that you can buy for just $19.95. And it's just a good solid piece of aluminum. And it works. It's a lot of money to pay for a piece of aluminum, but it works. It works really well. If you were to put a piece of frozen chicken on here or a frozen burrito, it melts it really, really quick, or dethaws it very quick, because the aluminum conducts so incredibly well. And that's this whole idea. Oh, by the way, silver even more so. I know that my wife and my sister, if they're in the snow or the mountains or skiing, they're always really careful never to wear the earrings that are real silver. They say it's just really, really painful because the silver conducts the cold so incredibly fast. So they make sure, okay, well, we'll do the stainless steel jewelry today because we're in the cold weather. And so they'll put in the stainless steel and say, okay, that'll keep my ears warm. But the real silver jewelry, it just conducts really, really fast. It kind of reminds me of when I do the dishes after a fancy Christmas dinner or an Easter dinner or a Thanksgiving dinner, because that's when we bring out the real silver. You know, not the stainless steel spoons, but the real silver comes out. So we polish it all up and we put it on the table. And then when you wash it all up, if it is hot out of the dishwasher and you pick it up, it's amazing how hot it feels. You pick up a spoon that is stainless steel, it doesn't feel nearly as hot. Is it? Is there really a difference? If you've never experienced that, let me ask you this. Have you ever gotten up on a cold morning and maybe stepped on carpet versus tile? Or maybe sat on a toilet versus stand next to the toilet? Does the tile feel the same temperature as the carpet? Does the toilet feel the same temperature as the air around it? So is somehow the tile colder than the carpet? No. It's the same temperature. But it's the rate at which the energy is coming out. And the conduction of tile, or the conduction of the porcelain, is much higher than the air or the carpet. And so what happens is you step on the carpet, and the heat from your foot flows into the carpet, and then it stays under your foot in the carpet, and now the carpet is essentially warm under your foot. And so you might not even notice it being cold at first. But if it's tile, you step on the tile, the heat flows out of your foot, goes into the tile and goes throughout the tile, and so it's still cold under your foot. And so the heat just constantly comes out, and to you, that thing seems colder. It's not that the temperature is colder, it's that your body puts out more energy. That's the difference. It's not that it's actually colder, it's that more comes out. And that's the same thing that I was trying to say with a silver spoon versus a stainless steel spoon. When I reach in there and get the real silver one out, I know that when I touch the edge of it, it's hot and the heat flows up. And then it continues to flow up. And so it stays hot. It's like, oh, 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 and I put it away. But the stainless steel one, I do this, and the heat right under my fingers flows into my fingers, so it's kind of warm at first. But then the heat in the rest of the spoon doesn't flow up very fast. And it doesn't flow into my hand, and it just doesn't feel as warm because I'm not getting as much energy. And so I'm trying to point out the difference between the energy and the temperature. I saw this when I was a kid. It was the worst scenario that could happen to somebody. I don't know if you've ever been out in the desert. We were in Palm Springs. We were in a hotel. We were running around the pool. We were barefooted. We were young and dumb kids, and there was an ice cream shop across the street. All we had to do was cross the street, go to the parking lot, and get some ice cream. So we're like, hey, let's go get some ice cream. So we left the pool and we started walking on the black asphalt, and it was hot. And so we're all, ouch, 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 and we get across the street and we quickly get into some shade. And then we realize that we got to go all the way through this parking lot in order to get to the ice cream shop. And so we're like running from shade spot to shade spot. And it's hot on the feet, but at least we're making it. Well, one of my friends steps on a manhole cover that's metal, that conducts the heat much better than the asphalt. And so as we ran across the asphalt and finally got to the ice cream shop, he steps on this manhole cover and just cringes with pain, limps over, and we looked at his foot and it just was all blistered. And we just couldn't really understand at that age why there was such a difference. And now it makes sense to me, is how quickly the energy transfers is the big picture. And that's what I'm trying to convey here. It looks like my chunk of ice on the aluminum is now completely gone and the wood is not. Well, this gives me a chance then to give you a formula that we're going to be working with. How quickly do these things conduct? And so our formula for conductivity is this: Q over T. So let me pause right there. Remember what the Q stand for? That's the amount of heat energy. And so this is the rate. How quickly does the energy transfer? Well, it depends upon some factors. Let me write them first and then show you a picture of what all of this means, because your author here is trying to say this is what it flows down. This right here is the energy per time as it flows down. This is the Q. How much energy? Okay? Then you can kind of see how much energy would flow would probably depend on a number of features. And this right here then is the temperature difference. How much warmer is one compared to the other? And so over here, we would have temperature 2 minus temperature 1. And so if there's a big difference in temperature, you would expect it to flow a lot of energy. Where if it's only a little bit, well, then just a little bit of energy. So that one is probably the obvious one. These other ones, I don't know if they're so obvious. That's why they deserve to be talked about. This is what we call the area. And your author doesn't really show it in this picture. I think he might show it in the next picture. Oh, there it is. It's this one right here. He says this is the cross-sectional area. And so back to my conduction meter over here, the energy would be flowing from one side of the rod down to the other. And so the area is the cross-sectional area of this rod. That's how much space the heat has to flow. And you can imagine that if more area, more would flow. If you doubled the area, you should double the amount of flow. And so that's why it's in the numerator. That's why we would call it proportional. The D is the length of how far does it need to flow. And so right here, he gives this D, and you can see that it should be probably inversely proportional. See how it's in the denominator? Well, this is saying that it's going to get harder the longer you have to flow. This is the same thing we saw with our fluid dynamics, that we had a greater loss in pressure the greater the distance it had to flow. So this is really the same as our fluid dynamics here, that it's just hard to get it to flow along this length here. And then this number, this K number, is actually a factor of the material itself. And so the other factors are what I call geometry. But this factor, which is the material, we call it then the thermal conductivity of it. How well does this material conduct? Thermal conductivity. And this is where a nice little chart comes into play, and we can look at some of these numbers. Here it is. Notice again at the top of this chart is the silver. And so silver really transfers heat energy really, really well. And so it's on the top here. You'll notice that I had the copper bar was the first one to make the wax fall off, and so sure enough, copper conducts very, very fast. So does aluminum and gold, but I didn't have those bars, although I did have the aluminum plate, so you saw that. Anyways, we can go down. Look at the stainless steel. You can see why I grabbed the stainless steel also. You can see it on that plate. Stainless steel is actually beating the wood, but I'm not sure I would brag about either one. They're just not that fast. There's nothing real exciting here about how quickly it flows. Although it does beat things like brick and water and glass, and so we're going to be using these numbers to calculate how quickly does energy flow from one spot to another. And so hopefully before today's over, I'll get a chance to do some more calculations here with you. But I do want to point out something that can be quite interesting. Even if it had a small thermal conductivity, if the length is really short and the area is really big, you might actually still be able to get a substantial flow rate through the material. And I think your author listed, I went past the table, but I think he lists paper here. Because I want to show you a little experiment, kind of a fun experiment with paper. He's got wood here. Maybe I'll treat 0.04. Oh, that's wool. Where was wood? Wood, here it is. 0.08, 0.06. I don't think he's got paper by itself. So I just want to point out that paper or wood, you can see right here with the wood how poor it is. But what if I just had one thin sheet of paper like this? And even though the conductivity of the material itself is pretty small, the fact that it's thin, it doesn't have much distance it has to go through. And the fact that the area is big could make up for that. Here's why I say that. Because most people when they take a piece of paper and they wrap it around a stick and they put the stick in the fire and it burns the paper, nobody's surprised. Everybody goes, well, of course you burn the paper. You got it hot, right? And paper, in case you don't know or don't remember from your high school reading, do you remember the book Fahrenheit 451? You still read that in high school? Is that the Ray Bradbury book? Some of you are saying yeah. Some of you are looking at me like I'm crazy. Okay, but anyways, so the sci-fi book, Ray Bradbury, Fahrenheit 451, is titled that because that's the temperature that paper burns at. And so it's a story about burning the books, okay, in case you're wondering, for those of you who haven't read it. All right, but to get paper to catch on fire, you got to warm it up to 451 degrees Fahrenheit. And clearly I did. But it gets real interesting when you take that same piece of paper and you wrap it around a metal bar, then you put it in the flame. Does it catch on fire? And now we're back to that same thing before. When you get up in the cold morning and you step on the carpet versus step on the tile, is there a difference? Well, there's not a difference in temperature, but there is a difference in feel because there's a difference in the rate at which heat is transferred out of your body. And I would say in this case, what's happening is this really hot flame is touching the paper, trying to warm it up, but I say try because it flows through the paper. Usually you don't think about that because, oh, it's paper, but if you wrap the paper tight onto the metal bar, then it can go into the metal bar, and the metal bar can conduct the heat away from the paper, and the paper never gets up to 451. Now, eventually it will. You can't tell, but I can feel this bar is already getting warm. And so as the heat flows into the bar, it flows through, and it flows down to my fingers. And so my fingers are starting to get warm. And so it'll take a while, but eventually this rod will get up to a high temperature. Maybe about 400 degrees, at which point the transfer of energy through the paper will not be fast enough, and the paper will get to 451, and then it'll catch on fire. But trust me, if this metal bar gets up to 400 degrees, I won't be holding it anymore, and I'll let it go. In fact, it's starting to get warm, so I think that'll be long enough, and you get the idea. It brings up kind of a fun question that also leads us into convection really well. Can you boil water in a paper cup? I mean, most people's reactions are, wait, that's paper. You can't put paper in a fire, can you? Well, let's talk about this a little bit, because this will lead to our second mechanism called convection. And hopefully, before we're done here, I will convince you that yes, you can boil water in a paper cup. And, oh, this would probably be a good time to stop for a break, but I just started the water. All right, let me talk a little bit more, and then we'll take our break a little bit later so we can see the water boil here. But what I'm hoping you begin to see in this is that I have the thin paper again. So there's my conduction, but I also have something helping me out called convection. And so let's look at the second mechanism. So the second mechanism, being convection, takes really Archimedes' principle into effect and the thermal expansion from the last chapter. So imagine me having a cup filled with water, which of course I do right over there, and I put a flame underneath it. And so I'll say, here's the level of the water. And I'll just say that at the bottom of the cup, it is very, very hot. And of course, if it gets above 451 degrees Fahrenheit, it's going to catch that piece of paper on fire. But fortunately, the paper is thin enough that, as we said back here, the thinness of it, even though the conduction rate is pretty slow, this is a small number, this is a small number also, and it's in the denominator, and I don't know if I'd call that a big number, but it's reasonably big. It's the bottom of the cup, and so the heat is transferring through, and it hits the water. Now I'm going to say the water is cool, at least it starts cool. Oh, and there it boils. And so I guess the short answer is yes, I can boil water in a paper cup. And what's happening here is the water that is right above the bottom begins to warm. And if we go back a chapter, when something warms, doesn't it get bigger? And if it gets bigger, doesn't its density go low? And if we go back 2 more chapters past that, what did we say was the condition for something to float? Doesn't it have to be lower dense than the stuff around it? And so I would say this warm water then rises. And so maybe you've heard that phrase, hot air rises. Warm water or hot water rises. I don't know if you've ever stood on a stepladder to maybe change a light bulb or to adjust the ceiling fan. It's amazing how hot it is up there. And because in this room, where does all the hot air go? Up. And I'm trying to say, if you put together thermal expansion together with Archimedes' principle, you can see why it goes up. And so what ends up happening is the warm water rises, which means the cooler water circulates around and goes to the bottom, only to be warmed, which keeps the circulation going. And so this is the definition of our convection. Our convection is that the energy is being transferred, not because one molecule bumps another one, but because that hot molecule actually moves. I would say right up there it is warm because this hot air went there. The molecules went there. The warm ones went there. And that's the difference between conduction and convection. Convection, the molecules actually move from one location to another. And of course they do that because of the Archimedes principle. Well, like I said, there's a lot to talk about this, but you guys deserve a little bit of break, and we'll come back and continue on. So let's take our 15-minute break, and remember the little boiling water, and we want to talk more about this and show you some pictures. All right. I'll see you from the break, and for those of you online, I just wanted to take a quick comment because we are kind of having a fun discussion here on the break that our boiling water in our paper cup, I might not have made it very clear. There's actually both conduction and convection going on here, and so the conduction is through the bottom of the paper cup, and so there is conduction, and so we have a very hot flame conducting energy through the paper cup. And that's what I was saying is it may sound weird that you can get so much energy flowing through paper which has a small conductivity, but it only works because we're talking about a really, really thin surface. So I do have the conduction. And the other thing that I should have overemphasized is that once it gets into the water and warms it, and I focused on the convection part of it, so it would warm, expand, and Archimedes' principle said it would rise, and so we get this circulation. And so we get energy near the top quicker than we would have than just conduction alone, and that's what the convection is. But I did want to say, as long as water was still in the cup, we know that the temperature is 212 degrees Fahrenheit from, our earlier discussion. And so we decided to kind of stop it a little short, and so most of the water is gone, but we thought it would be fun to continue the process. And I just hope now I can bring it back to a boil without burning the top part of the cup, because there's just a small segment of water there. There is no water protecting the upper part. In fact, you can kind of see the rim now turning black over there. And I might actually catch it on fire before I turn it back to a boil. Yep, looks like I'm gonna. I see it smoking. But I wanted to see it all kind of boil away, and then, of course, once it all boils away, you'd see the cup catch on fire. So maybe it'll just blacken, but not actually burst into flames. We'll just see how it goes. But my point was, I really wanted you to understand convection, and I have a couple pictures on a few other demonstrations here to show you. And so coming to your author, I guess this is number 17, your author says, this is a common procedure in houses where you'll have what they call a radiated heater or a fireplace or some object that's hot, because the idea is the hot air will rise, and as it rises, it will push around and circulate the cold air, and you just get this natural flow on its own. And so that's our convection. His other picture is really nice too, where he's showing the same thing I was trying to show with the water boiling in the cup, that you're just going to get this circulation, and so all the water gets to be the same temperature as long as it circulates around. But I thought I would use this as an opportunity to then talk about a common water heater, because maybe you guys are a little bit like me, where when the alarm goes off in the morning, you're like, oh no, it's way too early. And so when you get into the shower, maybe you take a longer shower than you really should, because half of it is kind of just wake up time. And what ends up happening is the water doesn't feel quite as warm about partway through a long shower. Now, not so long that it feels cold, but just not as warm. Because if you think about the design of a water heater, and so somewhere in your apartment or your house, there is this tank that underneath it has a flame. Now let's start there. Why did the engineers design the flame at the bottom of the water heater? Yeah, purposely, because hot water rises. And so the idea is the coldest water, and it may not even be cool or cold water, but the coldest in the tank is going to settle at the bottom. And so if you've been just sitting there all night long with this tank of hot water, the hottest water gets to the top, the coldest water gets to the bottom, and so up here is hot, down here is cold. If you look at the pipes come in, and so let's say this is the water coming in from the street, and so this is coming in from the water department, and so maybe it's kind of a cool amount of water, and then this is a hose coming out, and so this is the hot water going to the shower and the sink and the dishwasher and the rest of the house. But inside the water heater, this one actually extends all the way down to the bottom, and this one feeds off the top. Because when you get up and turn on the hot water, this is the water you want going towards your shower. That is the hottest water in the tank. And of course, as the water comes out, cool water is going to come in. And if you didn't have this pipe going all the way down, then the cool water would come in and it would still sink, but it would kind of mix. And that would cool the rest of the water. And so the brilliant design here is to say that as the hot water comes out, the cool water is going to settle in at the bottom. And there's kind of then this magical divide line between the water that's hot and the water that's cold. Oh, looks like all the water boiled away and it got on fire. Okay, good. Forgot about it over there. Okay. But then the cool water, of course, is near the flame, so it starts to warm up. But let's just say you're using so much hot water, more hot water at a rate faster than it can heat up. This level of cool water keeps rising. Now, if you take a really, really long shower, of course, eventually this cold water goes in this pipe and comes out the shower, and you're like, okay, I used all the hot water. I think it's time to get out. But even before that, maybe about halfway through, you'll start getting water that was in the middle of the tank when you started your shower. And that water's not as warm as the hot water. And so inevitably for me, I get in there, I adjust it, I get in, I'm still trying to wake up, it's nice and hot. About the time I wake up and finally really ready to shower and get the soap, I noticed it's not quite as hot as I wanted it to be, as what I started. And so I do a little adjustment and go, okay, then I finish up the shower. And that's because of the design of the water heater, and that the hot air, or excuse me, hot water rises to the top. And so again, the engineers have made a clever way of separating hot water from cold water, and using this whole idea of density and Archimedes' principle, and taking advantage here of the convection currents. Well, I better then get to something I think will be more useful to you guys, and that is the transfer rate when things are moving, and we call this a wind chill factor. And so, as you probably have experienced, if it is cold outside, of course, you're losing body heat, body energy, and it's conducting out and then warming the air around you. Now, if the wind's not blowing, then that air tries to stay somewhat close to you, maybe even get kind of trapped in your clothing. But if the wind's blowing, your energy that came out and warmed it then moves away, and more cold air comes in. And so it can just feel colder. This is our discussion about stepping on tile and stepping on carpet. It's not really that it's colder, but your body is losing energy at a faster rate. And that's what you're going to feel. And of course, if it's losing a lot of energy, that can be dangerous. And so we have what we call a wind chill factor. In other words, if it is a certain temperature outside and the wind is blowing, the effect on your body is as if it was a lower temperature. And so this is the convection in the sense that the wind chill factor. So I'll just pick a temperature, let's say it's 0 degrees outside, but the wind is blowing at 2 miles an hour, or meters per second. So, that'd be about 5 miles an hour. Anyways, it would feel a little colder. It'd feel like -2. Well, that's not a real big difference, but it's not much of a wind either. But as you can see, as the wind picks up, and especially a strong wind at 20 meters per second would now feel like it's -20 degrees Celsius. And remember, Celsius and Fahrenheit about a 2 to 1. So it's like it's like -3 or 4 or 5 on the Fahrenheit scale. It's cold. It is cold. Anyways, but that's kind of the chart I thought that you guys might appreciate a little more. Also, another picture I thought you would appreciate more had to do with convection is, how does fur work so well? How does the buffalo stay out there in freezing cold Montana and stay warm? Or the polar bear, there's a better one. How do they stay so warm? And fur is amazing for these two properties. One, and let me not take the time to go back to that chart of thermal conductivity, but if you look at the thermal conductivity, air is one of the least conductive materials there is. So it's kind of hard to transfer the energy between two objects when there's air in there. I mean, if you've ever stood next to something that is warm, you can feel it, and maybe you'll feel the radiation. That's our next discussion. But the molecules themselves bumping one to another is really at a slow rate. So air works really good. So Puffy jackets are puffy because most of it is air. Fur is puffy because most of it is air. However, the bad thing about air is it can move real easily. It can circulate. It can have convections. And so even though air cannot transfer energy very well by conduction, it does transfer it very well by convection. So if I just built, say, a house, and so here's a wall, and I put up a piece of drywall, and then I put some 2x4s, and I put a piece of drywall on the other side, or stucco on the outside, and there's air in between, my first reaction would be, oh, air doesn't conduct the heat very good. This will keep the house cool, or cool in the summer and warm in the winter. However, if all I have is a big column of air, then these eddy currents will form in here. These convection currents will form, and the air will start circulating around, and then that does transfer the heat really well. So the trick then is to stop those vection currents. And that's what the fur does. That's what the insulation, which is usually a fiberglass, does. It's just there to get in the way so that the air can't move. So you're trying to use the air as the insulating material, but you also need something to keep the air from moving and circulating, and so you put something very light and also doesn't conduct well in there. And so that could be feathers, that could be styrofoam, it could be hair. The list goes on, but this is what the author is trying to say. If you have a warm body and some cold air, the fur pretty much just traps a boundary of air in there, which means it doesn't conduct. And it keeps it from circulating. I still can a little bit, and that's what the author's trying to show with these little circulations. And so it's very effective. Feathers can be very effective. Fur can be very effective. Anything that just really keeps the air from circulating. So if you've ever laid insulation in your house, the fiberglass, it may come this thick, but if you ever push on it, it just shrinks up like that, because really what's insulating is the air. And the fiberglass is just there to keep the air from circulating around. Well, let me show you then the conduction, I think, in a neater form here. I'm going to get some hot water and some cold water, and I'll do it twice. And so hot water and cold water. And so you can kind of see what's happening here. I'm going to make the hot water red. And so we've added a little food coloring in here, and so the red is for the hot stuff. So let me start with a little bit of cold stuff, if you will. So I'll maybe start off with 2 flasks that are filled with cold water. Let me fill these with hot water, although, so I don't make too big of a mess, let me put them in a tray. And here's what I want you to see. I want you to see an important difference in the rate that energy transfers when you have hot on top versus hot on the bottom. And so let me start with the kind of the boring one. I'll call it the hot on top. So this will be my hot water, this will be my cold water. I'll put this on top. Let me kind of set this up, and so I don't burn myself too badly, let me get something to hold the neck. I got the hot water going here. I will pour in some hot water . And again, let me just top it up. So again, the red is hot. And what if I were to do something like this? I'll grab the neck. I prefer to go this way. Nope, not gonna do that. But so that hopefully I don't spill too much, I'm gonna put hot on top. And then let them at least have the possibility of mixing. But as we said earlier, hot water expands, it's less dense, it wants to rise. It's already rising there. And so I would say this is kind of boring. This is not mixing. The hot water is going to stay hot, and the cold water is going to stay down at the bottom and stay cold. There's really no convection going on. And so the rate at which energy transfers in a scenario like this is very low. However, let's reverse it. Let's put the hot water down at the bottom. And I'll just top it off so it's nice and full. And still hot. That was a little bit of cold water, but not much. And then if I put the cold on top of the hot, you will hopefully see the difference I'm trying to illustrate. And that is the hot is going to rise up. And you can see then it's starting to look kind of pink up here. And so this hot water is then mixing, and then the cold water is sinking, and this will not take long before they're at the same temperature, and they're both lukewarm. And so depending on how the hot and cold are situated, together with the convection currents, this process can happen slowly, with no convection currents, or quickly, with a lot of convection currents. And for better or worse, this equation that I gave you for the rate at which it conducts, we don't really have a good formula, because this is that turbulence. Remember the fluid dynamics we talked about and said, boy, if you have turbulence, it just becomes a nice mathematical nightmare. And so I guess in terms of taking a class and doing the problems and getting a grade, it's good news. We're not going to even try to give you a formula. We're not going to try to give a way to calculate how quickly this one reaches equilibrium compared to that one. Oh, we'll leave that for some advanced fluid dynamics, turbulence, Reynolds number, all those discussions. But what I do want to leave you with, and this is what the author does, is that convection currents you can understand conceptually. And just remember then that hot air or hot water rises because of thermal expansion and Archimedes' principle. And then depending on how much convection you have going on, this can take a long time or a short time. I should point out conceptually here, did you notice that convection then can only happen with a fluid? Right? It can only happen then with a liquid or a gas. You cannot get convection with a solid because the atoms have to actually move. So when we started this chapter, I was doing something like this. I was saying, take a warm aluminum block and put it next to a cold brass block. And I said one would bounce near the other. This would only describe conduction, but not convection. And so convection is a lot more complicated here. In fact, it kind of leads to what we call cooling fins. Have you ever seen scientific equipment or other equipment that has this on the back or on the front? These are called cooling fins. This little power generator, and let's not worry about what it does, but it's a little piece of electronics, and this could be as simple as your DVR player at home. It needs to cool itself. And in this case, the engineers have decided we don't need a fan blowing the air through. What we can do is just put holes in the top and in the side and a cooling fin in the back. And here's the idea, that inside of here there's a bunch of electronics and it's going to get warm, the air is going to rise. And if you put holes in the top, what happens to that air? It escapes out and then of course then draws in cool air. And so who needs a fan? It'll just circulate on its own. That is, of course, until somebody decides to say, hey, this is a nice DVD player or DVR player. I'll put that near my TV. Oh, and you know what? Maybe I'll put a plant on top of it. And then what have you just done? You've closed off that ability to circulate around. Or the nice little feet in the bottom. This one doesn't have it. A lot of them have holes in the bottom to draw the air through. And you decide, oh, I will just go ahead and put this on a soft towel or a thick cloth or carpet. And then again, what have you just done to your electronics? You've just blocked the circulation of the air. And the number one killer of electronics is heat. And so these are here for a good reason. And look at these cooling fins. Do you see how they are, number one, vertically. Number two, they're black. Number three, they're made out of aluminum. And so here is some cooling fins off an old, this was an old radio amplifier, but you mount them this way, never this way. Why? Well, they're made out of aluminum. They're mounted to something that's hot. Remember we said aluminum has a good conductivity, so it pulls the heat out into these metal fins. The metal fins get warm, and then what happens to the air that's kind of between the metal fins? It gets hot, and when it gets hot, it rises from the convection, and it goes up, and then brings in more cooler. So you don't need a fan to circulate it as long as you mount it in a vertical position this way. In fact, probably the only place you'll ever see cooling fins mounted horizontally is if that object moves, and then the wind blows that way. A motorcycle is a good example of that. Any air-cooled engine, like an airplane, is a good example of that, where the cooling fins are mounted this way so that when the motorcycle is moving, it will flow through. It's not using just the rising convection. In fact, that's actually really rough on a motorcycle, is to just be sitting here and letting it idle. It overheats. It's not designed for that. Which is, of course, why, or maybe you don't know, California law allows motorcycles to what they call split a lane. And so you go between the traffic. In case you were just thinking motorcycle riders are impatient, which that might be true too, but they are designed and legally allowed, and they're supposed to drive through the middle of traffic. The worst thing you can do on a motorcycle is sit there and just let it idle. The cooling fins are not designed for that, and the motorcycle will all of a sudden break down and overheat on you. Well, there's a lot more I could say about those, but I better move on. And that one, like I said, there's no math to that, so I think you'll appreciate that. It's just conceptual. Now, before I accidentally knock these down, let me take them down without hopefully burning myself. Let's see, maybe this one will be a little bit easier since it's already lukewarm. But before I take it down, I'll point that out. See how it's already transferred, and each of them are kind of a lighter pink, but this one's still hot and that one's still cold. And so if I hopefully take them down, and this one, let's see, it's going to be a little trickier being hot. Good. Not too bad. All right. So we'll call that good. All right. Now, the last thing, and the last part of this chapter, and maybe we'll get a chance to do an example or two, but the transfer of energy by radiation. And this last one, first of all, I think sounds kind of scary at first. You go, whoa, well, radiation. Because I think most people, when they hear the word radiation, they think of nuclear radiation or radiation associated with poison and things that will kill you. That's not what a scientist means by radiation. Anything that radiates, anything that gives off what we're going to call here electromagnetic or thermal radiation is our definition of radiation. And we're going to study this a lot more coming up. And so we really haven't studied much of it, and that's why I say this one's a little bit harder, I think, to comprehend. So I'm going to try this. Let's take the sun, for example. You know that we get sunlight from the sun. Something leaves the sun, it radiates out from the sun, and that's what we mean by radiation. The sunlight is the radiation. And if you were to go and look on the molecules or the atoms on the surface of the sun, we're back to this picture again. We're saying they're bouncing around. And like I said, we haven't got that far yet. In fact, this will be the study next semester for those of you brave enough to hang around and do the next semester. We're going to learn that if you have a charge, and I'll just say, here's a little electron from my atom, and maybe here is a little proton from the nucleus of my atom. And as they bounce around, they're going to give off waves of energy. This is our next topic, to talk about, well, what is a wave? And a wave, if you just take a moment and think about a water wave, it's the surface of the water going up or down. Since this is made out of charges, we're going to say it's made of electric fields. Now, again, it's a little too early to get too deep into the physics here, but I just want to say that something, and I'm going to call it then electromagnetic radiation, is coming from anything and everything that is made out of atoms that are bouncing around. And isn't that everything? I mean, most of us, when we think about the sun, we go, well, the sun is giving off this radiation, this solar radiation, because it is hot. And although that's true, I would say the sun is so hot that they move so quickly, and that's the range that your eyes are designed to see. But what about this warm red liquid? Is it made out of atoms? Are they bouncing around? Does it give off radiation? And I'm going to say yes to that, although it's not in the wavelength or the frequency that our eyes can see. So like I said, I'm a little bit at a disadvantage to try to completely explain this, but here's what I want to say. I want to say anything then that has temperature gives off these waves, these electromagnetic waves. They may not be so hot and moving so fast that you actually see them with your eyes. If you take a piece of metal and you put it in a hot fire, it will move so fast that then you'll say, oh, it's glowing, it's giving off light, it's red. But I'm going to claim that even before you could see it with your eyes, even something like this is giving off what we call infrared. We call it infrared because it's at a frequency, and that's because its temperature is low, it's lower than what our eyes can see. And what we're going to learn is our eyes, the lowest frequency our eyes can see is red. Your author does a pretty good job here to try to get you to understand by saying, let's take some pictures of different objects. And he starts with a fire. Well, it makes sense. There are parts in a fire that are so hot that the molecules are moving so fast that they're bouncing around at a frequency that you can detect it with your eyes. And so we would say, oh yeah, the fire gives off light. But I would ask right next to it, right here, which looks black to your eyes, does that have temperature? Does that give off radiation? Yeah, and we're going to call it a thermal radiation. We're going to call it an infrared radiation. Like I said, since we haven't studied this and you can't see it with your eyes, it's a little difficult to fully explain this. And so I'm just going to kind of show you a couple of pictures here. This graph is saying, let's take something that is hot. And they show you a low temperature, if you want to call 300 Kelvin low temperature. They eventually get to 600 here, or 6,000. And so 6,000 is the surface of the sun. And what it's saying here is it gives off all these different wavelengths with different amounts of intensity. And this little bar right here is the part of the bar that you can see with your eyes. And here's what I'm getting at. I want to kind of explain to you to think of radiation for right now, until we get a chance to study it in more detail. Think of it right now as just light. I'll call it light. Now, that doesn't mean you can see it with your eyes, though. And so call it invisible light. In fact, the best word is to call it thermal radiation. It is given off because it has a temperature. This one has kind of a warm temperature, so it would give off some radiation, and it would give off more than, say, this aluminum block, which is only at room temperature. And then even this ice, we would call giving off thermal radiation. Now, you might say, well, isn't the ice cold? Yes, but it's still much warmer than the absolute zero we were talking about. Right? On the Kelvin scale, this is 273. It's got to get a lot colder before they come to a stop. So they are moving and they are giving off some radiation. And what this graph is trying to show is that there's a whole range, and only this small window of a range is what the human eye can see. And so when we look at something like this, we go, no, not giving off any light, it's only reflecting it. But that's not true. If my eyes were different, if I had equipment that could actually then record it, I could see that there is given off. And so your author tries to explain this and then shows you kind of a photograph here and does a pretty good job of saying, let's take a photograph that you would see with your human eyes, but let's do what we would call an infrared photograph. Let's give off one that shows the full amount of radiation, even the stuff you can't see with your eyes. And of course, then they color code them. And so the yellow here would be more radiation than the blue. And so we would come to the conclusion here that the windows are warmer than the other part of the building. But what I want to get across to you then is this is a transfer of energy. If you've ever stood near something warm, like hot coals, the infrared radiation is very strong. And you feel that transfer of energy in the form of these electromagnetic waves, these radiations. It may not be warm enough that you actually then see it. You ever drive a car And then after you drive the car, you get out and you walk in front, right where the radiator is, and you'll feel like this warmth. See, what it's doing, think of it as a giant light bulb that is now radiating at you. And if you could see that with your eyes, that's what it would be. It would be giving off this radiation. And of course, you guys being in the life science know, rattlesnake comes to my mind right away, is that they have sensories for this. They can actually then detect that part of the electromagnetic spectrum that you and I don't have. Oh, that's why a rattlesnake chasing a mouse down a little hole is going to kind of think of that mouse as a big light bulb. And the little mouse can go back in the hole and back in a corner and hide and tuck. But from the rattlesnake point of view, it's like a giant light bulb. I can't miss you. You're giving off this incredible amount of electromagnetic radiation. And so all I got to do is follow the light, and there's my dinner. Yeah.
So like the difference between conduction and radiation is that conduction is when things are actually touching, but then with radiation it's like you can have distance, but there's still radiation.
Good. I'm glad you say that, because I'm going to jump on that right here. So I want to point out then that these waves, and again, it's kind of hard to describe because I haven't got there yet, but this is the start of next semester. These are waves not made out of atoms. There is no atoms here. So I think that's what you were touching on. This is very different from both conduction and convection. There is no need for molecules between us. So between Earth and the sun, there's this huge vacuum of outer space. There are no atoms. But yet we receive energy from the sun. And this is the way we do it, by radiation. And so radiation is different, very different than the other two, because no atoms are involved. There's energy in these forms called electric and magnetic fields, which we've got to study a little more. But yes, you nailed it just right when you said that they are different than conduction. You don't need any material in between. And so if I were to stand near the front of my car after driving it, the convection would probably warm the air and it would go up. And so if I'm standing to the left of my car, I probably don't even feel any of the heat by convection. I would probably have to get near my car and put my hand over the hood to feel the rising hot air for convection. Standing a couple of meters away, I probably only get radiation. And the conduction through the air would be so small that I wouldn't even feel that being a couple meters away. And if you removed all the air molecules, then you wouldn't have any conduction at all, or convection, but you would still have the radiation. And so this is the energy by radiation. Yeah.
If they're not atoms, so what are they? Are they like electrons?
They're not electrons, so they're not material. They're not electrons, they're not atoms. They are electric fields. And so what we're going to learn as we get started in the next semester is there's a lot to this physical world besides the material itself. Maybe a simple example would be what we would call a gravitational field. I would say that this right here is going to get pulled down from the Earth because of something that's right here. And it's not the atoms, it's the gravitational field. It doesn't have mass. It's a field. Well, I told you, it's a little difficult to explain and maybe even a little difficult to digest, but these are not atoms, okay? And so we can have from the sun to the Earth a gravitational field. We can have radiation, which is an electric and magnetic field. There's no atoms between us and the sun. But yet things still are part of outer space. They don't have to be neutrons, protons, electrons. There are other things, and we haven't got there yet. All right, so probably the best thing I can say is think of this as just light. Okay? Here's why this is important. Because what if I were to come over here and fill both of these test tubes with hot water? Now, of course, they're in the atmosphere, so there's nothing I can do about the fact that there'll be convections. But I'm going to argue that the convections will be the same on both. But I'm going to ask this question, and this is the lab we're going to do today. And for you guys online, it'll be a lab tomorrow. Will these cool down at the same rate? Notice one is a shiny silver and one is a black. Now, before I answer that, let me do myself kind of a test piece. And I like to just kind of warm up the tubes and then get rid of it. And then say, okay, let me warm up both test tubes. And before we get in a deeper discussion about these test tubes, let me ask you this. What if instead of filling it with hot water, I filled it with cold water and I went out into the sunlight? Would they warm the same amount? Would the silver one warm faster in the sunlight? Would the black one warm faster in the sunlight? Which one do you think would warm the fastest? Because then I want to ask you the harder question here, and that is which one cools the fastest? And so I'm going to start these at the best I can, the same temperature. And it looks like this black one is already a little bit cooler than the silver one. And so that's 70, and that's a little over 71. Let that go for a while. Let me just ask this same question. Black, white, go out that door, into the sunlight. Wouldn't you say the black one would warm faster? Why?
Because it's black, it's going to attract the light.
Okay, so what happens is the light comes, and that's it, the radiation. That's what I want you to think about. The light, the radiation comes from the sun, and on the black object, it gets absorbed. But what happened for the white object? It reflects. And so the black one is absorbing more energy than the white one. That's why if you're outside and you have a black t-shirt on, you'll feel a little warmer than if you have a white t-shirt on. And so keep in mind what you just said, right? The black absorbs the radiation, the white reflects. Because we're not out in the sunlight. We're in here. And the hot object is in the tube itself. And so imagine the hot radiation in the water trying to get out. It goes out and it hits the side of the test tube. What happens in the black one compared to the silver one?
The water will cool in the black one.
Right. See, the silver one, let me go the silver one first. I would say the silver reflects it back in. The silver traps that heat inside. The black one, as it comes out, it hits the walls on the outside, the black one, and it gets absorbed, so the outside walls get warm, which then lets it warm the air through convection a little faster. And so I would say the one that's going to cool down the fastest, and you, again, see it, is the black one compared to the silver one. That slight difference in reflecting the heat back on itself versus hitting the black on the outside. That's why if I were to take a thermos apart, what does a thermos look like? See how shiny it is? And that way, when I pour hot coffee into here, it tries to radiate and hits that shiny surface and reflects back in. And the heat gets trapped, the radiation gets trapped in there. Of course, to add to it, I have a wall here that perhaps is completely evacuated, like one of those hydro ones right there. Those are really nice, and they trap it in there because there is no molecules. There's a vacuum, there's two walls, and there's a vacuum. There's no way you can have conduction and convection when you got a vacuum between them, which is, of course, why you never put that in the washing machine, right? I mean, the washing machine, the dishwasher, because the heat is going to make things expand, and you're going to lose your vacuum seal on that. And so, big no-no to put those into the hot dishwasher. This one isn't evacuated, but it's actually, now it feels like there's a little styrofoam in between. But there's something in the walls to reduce conduction and convection, but there's also the shiny surface for the convection. Well, again, hopefully I talked long enough that you can begin to see they're both cooling down, but the black one's a little faster rate. And like I said, that's a little hard to digest, and that's why we're going to do the lab today. We're going to actually do a lab, and I don't know how best to describe this, but we're going to take some hot water, put it in a container. One container is going to be silver, one's going to be black. We're going to do another one that's white, and then we're going to watch it cool for a half hour. It's like watching paint dry. I mean, it's not the most exciting lab in the world, but we're going to measure it. We're going to see its rate of cooling down, and hopefully, even though it's only a small difference, because most of this is cooling down by conduction and convection, but there is slight effect from the radiation, and you can see it. And this is the hardest one for students to understand. Well, to finish the chapter then, let me give you the formula. This is called Stefan's law. Stefan figured out then, and maybe I'll go back to this graph. Well, there's his law right there. I'm going to talk about that. But it comes from this graph right here. And he says if you add up the energy of all of these waves, the ones that are in the visible and the ones that are not in the visible, there's a certain amount of energy coming from this object. So QT, the rate at which energy is leaving a hot object, is equal to, and there's some factors here. Let me start with the most important one, the temperature. And so, how much energy comes from a hot object depends on its temperature. And interesting, it's temperature to the fourth power. And so this is why, if you look at this curve, if we go from 3,000, and we get this curve, and so remember, this is the energy per wavelength on the vertical axis. So if I can dig down into your calculus, if you were to integrate that, so the area under the curve would be the total energy. Don't worry, we're not going to actually do the integral, but visually, if you look at the area under this, 3,000, that would be the total energy given off by this object. And look what happens when they double it. When they go from 3,000 to 6,000. 6,000 has a lot more area under it. Look what it says with the number. If you doubled this temperature, it would be 2 to the fourth power. 2 times 2 times 2 times 2. That's 16 times more. And so that's why objects that are just around in the room, really we don't feel much. We stand near this and go, do you feel any radiation? I can't see it with my eyes. Maybe I can feel the energy, like the warmth in my hand. No, I can't. But if we just warm up the temperature by striking a match and making a flame, that basically doubling the temperature, all of a sudden, whoa, yeah, that's really hot. I can feel that. I can get close to my campfire and I can feel all that radiation because it's 16 times more. So that's the big factor. Another factor here is, and I probably makes sense, is the area. And this would be the surface area of it. This would be saying, well, it radiates from every little speck of the object, so how big is your object? The bigger the object, obviously, the more radiation it would give off here. And so if this was the sun and I wanted to know how much energy was radiating from the sun, I would need the surface area of the sun, because the sun is giving it off all over the whole surface area. If it's this little experiment, I would say it has to do with the surface area of this test tube, which is why both test tubes, to compare them, would have to have the same area to make sure I'm comparing just the color of them, not the area of them. All right. Now, these other two is just a constant. This is called Stefan's constant. And this number is 5.67 times 10 to the minus 8 joules per second, meters squared, Kelvin to the fourth, to make all the units work out. And so as you do some examples here, we'll do that. And maybe the hardest one to understand is this number. It's between 0 and 1. It really has to do with this fact, is it black or is it silver? We call it the emissivity. In other words, we talk about how well does it radiate. Does it reflect it back or does it allow it to radiate? And so what we like to say then is something that is allowed to radiate the best it ever could would be a factor of 1. And anything that reflects back is going to be something less than 1. If it reflected everything back, it would be 0, meaning no energy would come from it. So this is a percent factor is what it is. It's a percent factor of saying how well does it radiate. Now here's the good news. As we do the homework problems, there's one that says the human body is cooling itself by conduction, convection, and radiation. And when it gets to radiation, it says your body radiates with an emissivity of, and I forget the number, I want to say 85%. So what they're saying is put 0.85 for that number, okay? And what we're going to do in the lab is we're going to see that this one radiates more than that one. And so its emissivity factor is closer to 1 than this one. This is probably somewhere under a half, and this is something over a half. Now, one last thing, and we'll call it quits here for today. Keep in mind then that this, well, maybe I'll write it over here, is happening for every object. So if I were to take, say this is a hot object, and I would put it in this room, I'll just put it right here, and I want to look at how quickly does it cool because of radiation, you need to remember that the walls in this room, you in this room, the table in this room, are all radiating at it. So as it radiates energy outward, more is coming at it. So if you wanted to see the net rate, you would say Q over T leaving the object minus a Q over a T coming from the environment, coming from the room. And so if we apply this equation to both the object and the room, we're going to get Stefan's constant times the emissivity of the object times the area times the temperature to the fourth of the object minus Stefan's constant, emissivity, area and the temperature of the room. Now, we can kind of simplify this by recognizing that the area that absorbs the radiation and the area that radiates it for this object are the same. So it gets absorbed and radiated on the same surface area. And so I can factor that out. Stefan's constant I can factor out. Now, one thing that's not so obvious, but I'll just say it, is that the elasticity of it is the same, that it radiates as it absorbs. So I'll say that's the same. And so what we end up with is the net effect for any object is related to the temperature of the object and the room. So notice if the object is warmer than the room, it will have a net radiation effect and it will cool down. But what if the object is colder than the room? Then the room will actually start to warm it. Not by conduction and convection, but probably that too, but by just the radiation. The hot shower I mentioned earlier, and then we'll close, is a really good example. Again, when that alarm goes off in the morning, I kind of stumble out of bed going, I can't believe it's morning already. And I get into the bathroom, and before I actually turn on the hot water, it's feeling kind of cold in that bathroom. And I would say it's because my body is warmer, not only than the air, so there's the conduction and convection, but my body is warmer than the walls that are radiating at me. And so I radiate more energy from my body than the walls give back to me. And then I take this hot shower. And the mist flies around the room and lands on the wall and warms the wall. And sure, it warms up the air too. But if this is a hot, long shower, the walls are actually now warmer than my body. And so even after I open up the door and let all the hot air out, it still feels warm in that room because the walls are radiating more energy at me than I am radiating back out at the walls. Normally that's not the case. Normally bodies are warmer than the walls. Well, there's a lot more we could say about that, but we better not. So we're out of time. We'll call it quits. We'll call it the end of the chapter. We will see you guys over in lab at, it's called 11:15. Give you a 20-minute break, and then we will start watching our water cool for a half hour. All right. See you in a few minutes.